In this video, we'll talk about what the seasons are not caused by and what they are caused by. And I just picked Chicago for purpose of illustration. This is a Northern Hemisphere video, however. And let's talk about the Earth's orbit. So the Earth's orbit is not a circle around the sun, it's elliptical. So sometimes we're closer, sometimes farther away. The minimum distance is 1.47 times 10 to the 11th meters, and that actually occurs in January. And our maximum distance, 1.52 times 10 to the 11th meters, that's in July. The solar constant is about 1,000 watts per meter squared on the surface of the Earth. When the Earth is 1 AU away from the sun, that's 1.496 times 10 to the 11th. You'll notice that's in between these two values. So even without doing a calculation, the Earth is closest to the sun in January, but Northern Hemisphere has its coldest weather. So, and furthest from the sun in July, and we're hot in Chicago in July. So that should clue you in that the distance to the sun does not control the seasons. And a few calculations I can put together with this. So if we want to know what the solar constant would be in January, the solar constant varies as 1 over r squared, where r is the distance from the sun to the Earth. So if the Earth is closer, we'll be dividing by a little smaller number, compared to when the Earth is further away, we'll divide by a larger number, and the solar constant will get smaller. So let's see how that occurs here. So the 1,000 watts per square meter, that's at the reference distance of the 1 AU, so that's I have on the top. And here I have the close, the perihelion distance, 1.47 times 10 to the 11th, and that gives us 1,036 watts per meter squared underneath the atmosphere. Outside the atmosphere, it's a larger number, but underneath the atmosphere in January, we have more energy than in July. So a similar calculation, just putting in the distance from sun to Earth in July instead of January. And we get less solar energy. The solar constant, if you want to call it that, is smaller in July. And I went ahead and calculated the percent difference. So it's about 6.5% less solar energy in July. And then taking a look, just some hypothetical temperatures. These are not average temperatures, but more extreme temperatures. For a high temperature of the day in July in Chicago, let's say 100 degrees Fahrenheit, I've converted that to Celsius. It's 37.8. And then converting to Kelvin, I have to add 273. So we get a Kelvin temperature of 310.8. The Kelvin is the more scientific temperature that's more useful for comparing temperatures. The January temperature, 0 degrees Fahrenheit, converts to negative 17.8 degrees Celsius, and adding 273 gives us 255.2 K. And finding the percent change in the temperature, it's 18%, but these are in opposite directions. This would imply that we ought to be cooler in July. That's not true. Chicago is warmer, and it's warmer by 18%. So roughly. So there we have some reasoning that the distance to the sun does not control the seasons. Let's look at this a different way. If we think about the solar energy going through 1 square meter, and imagine this coming down to the Earth. The Earth is a sphere. So I've got a couple of drawings here. We're going to work on the left first. And this Earth, 42 degrees is the latitude of Chicago. Coming up to Chicago, I've got a straight line here that would be the horizon, and directly outward from the center of the Earth through Chicago to the zenith on the sky. At Chicago, the sun is over here to the left, and in July, the sun is closer to the zenith. In January, the sun is below the zenith, and really I should use the solstice date. So June 21st and then December 21st, we're 23.5 degrees away from the celestial equator for the position of the sun. So the Earth has an equator that goes out to the sky. We can draw a parallel line that also would go out to the celestial equator. And the sun is 23.5 degrees above the celestial equator in July, and it's 23.5 degrees below the celestial equator in, I should have said June up here, and 23.5 below in December. To find out the angle that the sun has from the zenith, well, 42 degrees is the latitude of Chicago. 42 degrees is the angular distance of the zenith to the celestial equator for an observer in Chicago. To find the angle of the sun away from the zenith, well, 42 degrees takes us down to the celestial equator. I need to go back 23.5 degrees to come up with 65.5 degrees for the angle in December. Sorry, I should have started on this line down here. 42 degrees minus 23.5, the sun is 18.5 degrees away from the zenith in June. In December, 42 degrees down to the celestial equator, another 23.5 degrees down to the position of the sun on the sky. So we have 65.5 degrees, this larger angle, down to the sun away from the zenith. Here's the square meter. You have to imagine this 1 square meter of energy coming down and hitting the ground in Chicago. I think you'll agree that if we were at the equator in March or September, the 1 square meter out here in space would cover 1 square meter down on the ground. There'd be no tilting of the ground away from the direction this 1 square meter is facing. In fact, the sun being away from the zenith, we're going to have an angle that the sun is away from the zenith here in a right triangle, and this 1 square meter of energy gets spread over a larger area that goes out to here. And my drawing is not the best, but kind of like this. So the 1 square meter that's here gets spread out over a larger area. The 1 meter width stays the same, but this side of a rectangle now depends on the angle away from the zenith. So in a right triangle, if theta is here, the definition of cosine theta is this 1 meter adjacent side divided by the length of the hypotenuse. I want to solve for the length of the hypotenuse. I do so by taking 1 and dividing by cosine of theta. So in December, that's 1 over cosine of 65.5. This solar energy is spread out over a rectangle that's 1 meter wide and 2.4 meters long. In June, the solar energy is spread out over a rectangle that's 1 meter wide and 1.054 meters long. So not much different. To calculate the area, this, of course, is going to be 2.41 square meters in December for that energy to cover. And in June, it's going to be 1.054 square meters. So let's see what that effect has on the energy. So I'm using this adjusted solar constant. This was for January, this is December, but it's close enough. The point is that in December, the solar energy is delivering 430 watts per square meter. In June, the sun is delivering 919 watts per square meter. So much more energy in June per square meter than we have in December. And this leads to the seasons. There's another important effect that I'm not going to cover. In December, the sun is low in the sky, rises in the southeast, sets in the southwest for Chicago, and does not spend as many hours above the horizon as it does in June. In June, the sun rises in the northeast, sets in the northwest, and stays above the horizon, delivering energy to the Earth for a longer time, much longer time than in December. That also has a good a great impact on the temperatures being warmer in the Northern Hemisphere in the summer. So 2 reasons that we have seasons. In December, we don't have as much energy per square meter, energy per second, the watts per square meter being delivered, and the sun is above the horizon for a smaller amount of time. In June, we're getting a higher value for the watts per square meter, and the sun is above the horizon for a longer time. So I hope that helps you think about why we have seasons. It's not the distance from the Earth to the sun. Instead, it is the fact that the angle of the sun changes with the seasons, the angle away from the zenith, and the energy gets spread out more in the winter months. If you want to see some more of these type of videos, go to my websites. This is free, no registration, but there are lists of the videos here with descriptions, how long they are, and you're welcome to subscribe to my channel. I'd appreciate it if you'd subscribe to my YouTube channel.